Welcome to this installment of Fun with Algorithms. I am Tess, I'm a developer at Microsoft, and I might be a little bit more excited about algorithms than the average Joe. I hope you are too, because that's going to mean we're going to have fun for the next hour or so. About 2 years ago, actually, this guy over here, Dylan, introduced me to this site called Advent of Code, which has like super fun algorithm puzzles throughout the month of December. And that led to a series of events that led to me doing competitive programming and a couple of things like that. But yeah, generally getting even more interested in algorithms. I think they've gotten a little bit of a bad rep as something that's only used during interviews. Because let's face it, maybe not all of our days look like this. At least not mine. I wish they did. I honestly wish they did. But they do look a little bit like this. Like a lot of pre-processing of data and things like that. And all of those build on the algorithms that we're going to talk about today. But today we're going to talk about a little bit more basic, fun algorithms. So did I say they were fun? I hope you think they are too, because that's the reason I hope you're here. So we're going to start off with, we're going to go through a series of like big blocks of algorithms that you can use as the basis and then kind of use them as Lego pieces to build up bigger algorithms. And we're going to start off with a game. And this game is, I'm thinking about a number between 1 and 100, and you're going to guess which number it is in the most optimal way so that you have to perform the least guesses as possible. You with me? So what would your first guess be? What would your first optimal guess be? Anyone? 50. Everyone knows, yeah. So 50 is definitely the optimal guess. Why? Because it evenly divides the problem space into two pieces. So when I say, when you say 50, I say higher, we've already eliminated number 1 through a 50, right? And then we can go through and follow up with this, and we say, you know, we divide it again in the middle, say 75, I say higher, 88, I say lower, 81, higher, 84, higher, 86, and so on, until we find like the perfect match, which is 85 in this case. That's the number I was thinking about. Now, this took 7 guesses. This turns out to be the maximum number of guesses that you will ever have to guess if someone is thinking about a number between 1 and 100. But we'll get there in a second. This algorithm that we just kind of invented, or that we've known from when we were children almost, is an algorithm called binary search. And it's a very, very powerful algorithm that can be used in many ways. Why is it so powerful? Well, if we would have done what's called a linear search of the data, if you would have said 1, and I would have said higher, and then 2, and then higher, you would have had to ask me 86 times or 85 times before I got the number right? In fact, worst case scenario, you would have had to ask me 100 times, because this is something called an O of n algorithm. It's like whatever the number space it is the maximum number of questions you have to ask me. However, in the case of the binary search way, where we guessed 50 and then 75 and everything, we have to guess a maximum number of 7, because if we look at how we divide the space and look at like 2 to the power of 6 is 64, 2 to the power of 70, or 7 is 128. Somewhere in between there lies 7, or lies the number that will be the actual maximum number, 664. But we can't guess 664 times, so we have to guess 7. So this is our maximum number of things. Now, we think, OK, so 7 versus 86 are actually 100. Computers are fast. Why do we care? This is, I mean, they can equally easily process 7 versus 100. But what if it's 1 million? Then it turns out that it's a difference between 1 million and log 2 of 1 million, which is 20. And if it's 10 million, it turns out that log 2, the maximum number of guesses I have to make, is 29. So 10 million versus 29, now we're talking, right? So this matters in the big scale, when we have big numbers to guess from. So this binary search thing is something that you can use in any kind of sorted space. Like you want to see if a number exists in a sorted array, we do the same thing. We take the lowest and the highest index, we take somewhere in the middle, and then we say, is it lower or higher? It's lower, so we now change our search space. And finally, we end up quickly at the right number. But this is like interesting, but a little bit boring. So now how can we apply this to some really interesting problems? Like this leet code problem, and don't feel like you have to read all this. We're going to go through this with pictures and things. But this is a medium leet code question already in the first 5 minutes of the talk. So we have our friend Coco, the monkey. She likes bananas. Surprise, surprise. And she gets a pile or a number of piles of bananas from her keepers at the zoo. These piles contain some number of bananas each. And they say, we're going to be back in 8 hours, and you need to eat the bananas. Okay. Now, she likes to savor her bananas, so she likes to eat them very, very slowly, but fast enough that she can eat all of them before the guards come back. She also has another quirk. She'll only eat bananas from one pile at a time, so we can't just take, whatever the sum of the numbers and divide it by your hours. So let's say, for example, she eats 2 bananas per hour, then it will take her a total of 15 hours to eat the bananas, right? Clear so far? If she were to eat 3 bananas per hour, we can sum it up and we can find out that she can eat them in 10 hours, still not good enough, or 4. And now finally we get to a number. This is like the lowest number that we can get to where she can eat the bananas. Like this is the slowest speed where she can eat the bananas and still get here. So this is us doing linear search through the speeds. Well, it turns out that Coco is a little bit out there. She has, she'll get like up to 10,000 piles of bananas. And each pile of bananas can contain 1 billion bananas. That's bananas, I would say. I'm thinking, like, at this point, this might not be about Coco and the bananas. This might be about, running tasks on Azure Batch. But we'll keep it to the Coco and the bananas, because that's a little bit more fun. So how do we deal with this? Because now, if we go through this and we look at this, how many actual operations do we have to make here? This is going to be horrendous. Like every sum that we're doing, we're summing over like a maximum of 10,000 piles. And the maximum speed that we could foresee is actually the maximum number of bananas in a given pile, because in this example, if we were to go anywhere over 11 bananas per hour, we could still only eat the bananas. We could still only eat one of the piles in 1 hour. So we know that the lowest is 1, the highest is 1 billion, and we have to iterate over 10,000. So if we would do it the normal way, we would end up with a potential of like 10 bazillion calculations. I don't even know how to say that number, but 10,000 by 1 billion. But what if we did it with binary search? Now it becomes a little bit interesting. So what we do here is, this is summing up the hours over the piles, and then we use this binary search pattern of, if we found a speed that's, that doesn't take us there, we have to increase the speed. Or if we found a speed that's good enough, then we know that the speed that we're looking for is between 1 and that number. So we can use the same technique that we use when guessing the numbers to narrow down the speed that Coco needs to use here. And this now takes us to what? It takes us to a calculation of, like a maximum calculation of 10,000 by 29 versus 10,000 by, actually, it's going to be a lot more because a billion would be more than 29. Sorry, I calculated that wrong. But literally, it will be like a huge improvement over like doing it the linear search way. So this is where binary search becomes interesting when you're when you're looking through large spaces, but it doesn't have to be as boring as a sorted array. You see in the pictures that I've used this O of something, and I'm sure a lot of you know what this is, and that this is called big O notation. So I'm not going to go through a full course of like what a big O notation is, but big O is a way for us to compare algorithms, roughly compare whether one algorithm is better than the other, just by how many iterations we have to make through the data. So if we have a list of fruits, and we go through the fruits, we have a loop that goes through the fruits, this is called O of n, because it's linearly related to the input size. That means that if we have 100 items, we do 100 iterations. If we have 1,000 items, we do 1,000 iterations, and so on. If we do a double loop, it's going to be n squared. It's very easy to understand, I think. But this is very rough, and this is talking about like the worst case scenario. Now, if we do something like this, we just print fruit salad that has nothing to do with the fruits in the thing. That's called a constant. So it's constant. It's not related to the number of items in the list. Even if we print like 5 things, it doesn't matter. It's still constant because we don't care about coefficients and things like that. We already know that if this was a sorted array and we wanted to binary search through it, we have log of n, which is very useful. Would it be better if we sorted the array and then did binary search if we had an unsorted array? The answer is no, because sorting also takes a lot of time. In fact, it takes more than just searching through the array. This is just for you to know that even like built-ins have a cost. So just for a comparison, this is like what you're looking for if you're looking for an algorithm that performs at log of n versus n2. Basically, if you find an algorithm that is at n, that's a pretty good algorithm in most cases. If we did something like this, if we want to know if peach is in fruits, then this is actually an O of n operation. We have to go through the whole list to figure it out. If we're using a list. However, is there something we can do here? Anyone? Yeah, using a set or a hash table or a dictionary or anything like that, we would have a constant lookup. So whenever you have a situation where you want to be able to quickly look something up, then using a set is a million times better than using a list, especially if you have a large list. If you have a small list, it doesn't really matter. Which brings us to data structures, which is one of the biggest things to look at when, and like one of the biggest choices that you can make when you want to optimize something. So if we have a dictionary or a set that has a constant lookup, meaning that they're super good for when you want to throw something in and find out if an item is in the list or in the set or in the dictionary. However, why don't we always use dictionaries or sets? Because dictionaries or sets don't allow us to have an ordered number of elements. So a dictionary or set doesn't have an order, and oftentimes we want an order. It matters to us which one comes first and last. It also doesn't allow us to have duplicate items, which is another reason why we would have a list. And it requires us to have something called hashable items, which means integers or strings or things like that we can create a hash of, not an object. That is not something that we can have in a dictionary. An array or a list can also become a stack. It is, in fact, a stack by default if we pop from the back. I'm saying this because oftentimes we want to have something else where we want first in, first out situations. And then we can use a neighbor of the list, which is called a queue or a double-ended queue, or a heap. And by the way, the pop left and pop right are usually a constant operation as well. Or a heap where we can get like the minimum or the maximum value fairly cheap. Or we can do like a sorted array, which is quite expensive compared to everything else because it needs to keep sorted, and therefore it also needs to do a lot of work to keep sorted. And then we have a very, very special kind of data structure that's called a graph. And this brings us into the next big set of algorithms, and I think the ones that are my favorite, to be honest. So we're all using graphs somehow in our applications, I think. One example of a graph might be friends on Facebook. This is called an undirected graph because we don't have sort of like, if I'm friends with you, you're friends with me, there is no direction to this, or at least there's two directions. Basically, it goes both ways. Whereas, for example, if we have something like a Twitter group of friends, then this is a directed graph because we might all be following Beyonce, but she ain't following none of us. Well, I don't know, maybe someone at the top, but not me, she's not following me. So this is a directed graph. We can also have a graph, for example, in this case, a graph of cities where the nodes, and these are called the nodes, are the cities, and then the roads are the edges in the graph. And this is a special graph because it has weights. So the steps between two nodes are not equal. Instead, they have different lengths, and this is important for when we go through and find like shortest paths and things like that. And this one also has a cycle. So here, for example, if someone says, take me from here to here, we might get stuck in this cycle. Actually get stuck there forever if we don't take care and check our, and remember what we visited and things like that. Yes, another set of weighted items. So this is like a set of tasks. In this case, and this is called a disjoint set because it has like two groups. So not all of the items are connected. And we can have other things that don't look like graphs, but there are graphs. So this is a typical thing that doesn't look like a graph, but is a graph, where every path that you can walk in this maze is a node, and every neighbor, so every other square that you can get to, is has one connection between them. But you wouldn't necessarily build this up and write like, okay, so there's connection between 0, 0 and 0, 1, like those indices. Instead, you would kind of like figure that out on the fly. And then you might have something like a chessboard with a horse where its neighbors are not the neighboring squares, but the other squares that it can get to. So this is also a graph. Some special graphs, trees, and even more special trees, binary search trees. So these are super useful, for example, if we want to be able to sort a set and quickly figure out when something is lower or higher. So in this case, we can see that everything to the left of the 8 is lower, and everything to the right of the 8 is higher than the 8. Or if you see someone on Twitter that says, yeah, I'm not interested in algorithms, I've never used a trie. They might have, because a trie is a very special tree that's used when you do, for example, ASP.NET routing. So a trie is a tree where you start typing something in this case, and the only options that we have are A or B. Those are the only valid starts of our route. And then if you've typed in A, the only valid next option is P, else it's not in your dictionary. And finally, if you type in a P again, like it's listing it as a valid word. So this is like a valid path or a valid dictionary word. So this is a super, super quick data structure to use for these kind of like pattern matching or route creation. And then linked lists is another good one. So you might think, okay, so they look good on paper, but how do I actually, represent them in anything that's useful for a computer? And one way of representing them is through an edge list. So this is just listing the edges, that there is like, a road between Oslo and Stockholm and one between Oslo and Copenhagen. You could even add, and don't worry about like the kilometers, they are not correct, I know that, but I just drew something super fast. And then, but you can put in an edge list also the weight of the rows between them. This is useful because it's very compact, but it's not useful for iterating through the graph in any way, because it's hard and it's costly to go through and say, what are the possible other cities I can reach from Oslo, for example? So then you build something called an adjacency list that looks like this. So this is just basically a dictionary that has, for every node, which other nodes that you can get to. And similarly, if you want to add weights, you could do this. OK, enough about data structures. Let's get into some algorithms again. So one of the most important algorithms when it comes to graphs, and I will just reiterate this, graphs are like everywhere. You'll use them all the time. So it's quite, for me at least, I think it's quite interesting to know these graph algorithms. The first one is depth first search. I'm sure you've all, at some point, written a depth first search, whether or not you know that it was a depth first search. So what we do in this case is we go from the start and then go to a neighbor or a child, and then we go to its child and its child and its child and its child and so on until we reach our goal. So this is like you go the deep way first. This is a good way of iterating through a graph, and if you find a dead end or something, you can then backtrack to where you found like a bend in the road. We can quickly make this into another, maybe even more useful algorithm by changing the stack into a queue. So in this case, first in, first out. I want to also mention that we're keeping a list of visited nodes here, so we don't end up doing a loop. But the breadth first search has a very, very nice advantage. So what it does is, instead of going deep, child, 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 it says, I want to see all your children, all its children, all its children, and all its children. And the neat effect of this is that it will quickly find the shortest way, the shortest path to your destination. So it will always find the shortest path to your destination. And it's a very, very easy to conceptualize algorithm, I think. So if you ever have a situation where you need to find like the shortest number of steps or the shortest path or whatever, breadth first search is your friend, especially if you don't have weights. Now, you might have a variation of this if you're trying to solve a maze like this one, where you have a key that you need to get to before, so you can unlock the door. In this case, you just think about nodes not only as coordinates, but as coordinates plus whether or not it has the key or not. So every square is actually 2 nodes in this graph. And then finally, if we have costs or if we have weights, we'll need to use other types of algorithms. I'm not going to go through these, but there are also like Wikipedia search away and very easy to implement. Dijkstra and A*. So Dijkstra is a greedy algorithm that quickly finds the fastest or the shortest path, the least costly path from one node to all other nodes. A star is an algorithm similar to it, but that has some kind of heuristics. So in this case, for example, for the roads, it might know that to go from Stockholm to Copenhagen, it needs to go south. So it will favor the roads that go south, for example. So you add in your own heuristics to figure that out. So that's a speed up or an optimization of Dijkstra. And then if you have negative weights, then you need to use another algorithm like Bellman-Ford. But let's have a look at, again, this breadth first or depth first search and how we can use this for other type of problems than fastest path or shortest path. So in this case, we want to know how many sets do we have, or maybe the size of the sets. And the way we do this is we start off at one node, and we go through and do a full depth first search to until our queue is empty, and we put them in a visited set. So this now becomes one set. Next time we look at another node. This is already in the visited set, so we ignore it. This is already in the visited set, so we ignore it. This is already in the visited set, we ignore it. We get to a new one. Now we have two. And this is like a very simple way to use DFS to figure out how many groups we have. So this is something we can use, for example, if we have a set of cities and we want to know, should we build a road between them, or should we have an airline route between them to be able to connect and get to all the different cities here. Another interesting base algorithm for graphs is called union find. So union find works in the way that we start off with all the nodes as separate. So even if they have connections, we start them out as separate with themselves as roots. And then we take one and we look at its neighbors, and then we try to connect them. So in this case, we say that these 1 and 2 now gets the same root as 0. And then we go through its neighbors, and we do the same. And if this neighbor already turns out to be a part of another set, we join the set. So we change the root of all the items in the set. This is a good algorithm for sort of figuring out both how many sets you have, and you can go through, for example, like this table now at the bottom, and see, quickly see how many of the items have the root 0 and how many items have the root 4, because that will tell you how big the sets are. So there are a lot of different questions that will come up that will basically come down to count the number of sets or count the sizes of the sets. And finally, one final graph algorithm is a topological sort. So a topological sort works like this. Let's say you have a set of steps that you have to do in a recipe, or a set of classes that you have to do where this one is prerequisite for this one. And we want to know in which order do you have to take all these, or in which order do we have to perform all these tasks in order for this to work out. So that's sort of like the question we ask. And this one works like this. We take any of the nodes that don't have any neighbors, and we write them out. Then we kill the links to them and find out what nodes do now not have any neighbors. We write them out, kill the links, and then we take this last one that didn't have any neighbors, and we'll write this out. And this now becomes a reverse topological sort. So you can see that all of these algorithms are fairly intuitive and simple once you start thinking about it. In fact, once you start doing them a few times, they become a lot less, wow, the guy came up with topological sort. No, it makes total sense how you do this once you start doing this. Okay, so that was all about graphs. Now we're going to go into another topic that's one of the favorites of these Twitter people, well, I haven't used dynamic programming in any of my coding, Well, guess what? You have. Because dynamic programming is just another way of saying caching. It's a fancy way of saying caching that makes you feel like a little bit better than other people, but nonetheless. The way dynamic programming works is like this. We have, everyone knows what Fibonacci is? Yeah? Okay. Great. So at some point you've done some recursion. So the way Fibonacci works then is obviously you take the previous number and the previous number, sum them up, this becomes your number, your Fibonacci number. And it looks like this, and it's the first recursion question you'll probably ever get. Now, a little problem with Fibonacci is that if you want to calculate Fibonacci of 5, then you have to calculate Fibonacci of 4 and Fibonacci of 3. And then it goes like this. And you'll see that there is a lot of repeated calculations in here. In fact, if you go to Fibonacci of 50, you'll have so many repeated calculations that you can end up spending a full day doing this before you're calculating the number. So obviously, we don't like repetition. And the way we can get around this is by caching these values. And this is what dynamic programming is. So we call this memoization because we need another fancy word for caching. So this is the original, and this is the memoized version. So the only thing we do is we say, hey, have I seen this n before? Then you just take it out of the cache. If not, then use it. Now, if we're doing this in Python, we can even just do this. Like just put on a cache directive. Obviously, there is a memory trade-off here. Like it's going to store all the results in memory, but this is a very useful way to even, like in any APIs you might have or anything like that, to just save yourself a lot of computing if you're doing a lot of repeated tasks. There's another fancy word for this, for doing this slightly differently. It's called tabulation. And in tabulation, instead of doing it sort of like the cache way, like putting the cache directive and everything, what we do instead is we're doing the iterative way without recursion, but we start off with creating a list of the things we know, and then adding on to the list like the next number and the next number and the next number. We can also optimize this a little bit because we're only using like the last and next to last number, but the idea is anyways that you start building up a set of results. So let's use this in a little bit more interesting problem, or we have a house robber. So this is again a medium leet code question. And the way this works is the house robber robs houses and he gets loot. So the first house here has 2 loot, and then the second one has 7, and so on. And he wants to maximize the amount of stuff that he gets. He has a caveat that he cannot rob 2 adjacent houses because then they will call the police or something. Normal stuff. Like there's a lot of this stuff going on in leet code questions, I have to say, but I think that's also what makes them a little bit fun. So one way we could solve this is brute force. We could say, what are all the combinations? And I didn't have time to write out all the combinations for 5, so I wrote out all the combinations for 4. But I hope you kind of like stay with me and understand. So now, 1 is I rob the house, 0 is I don't rob the house. So these are all the combinations that we could take. We can exclude the ones that have adjacent houses. That's fine. And we can now sum up all the loot from all the houses that we picked. Great. This will take us, for 100 houses, 1.27 by 10 to the power of 32 operations. That's a little fresh, I think. So maybe we can do better than that, because that's not really viable, I don't think. So let's think about this a little bit. When we come to house number 1, we have 2 choices. We can either rob it, And then we can't rob until house 2, or we can not rob it, and then we can rob at house 1. Right? Everyone in? So that means that if we think about it, our max loot means take the loot at 0 plus whatever max loot from 2 on, or take the max loot at 1. And this will be your maximum amount. And now if we look at this, doesn't this look a little bit like Fibonacci? In fact, very much like Fibonacci, I would say. So we can simply do some dynamic programming on this. And in fact, if you can turn anything into a recursive function, that where the input value, like in this case, or the input values are hashable, you can use dynamic programming to solve this. And remember when we had like the 127 to the power, like times 10 to the power of 32? This is 100 for 100 houses instead. Now that's a pretty nice and sweet improvement. So even in your APIs and everything, I think that dynamic programming and caching of this in this way has a place. Now, the last type of algorithms I want to go through is a subset of dynamic programming that are called sliding windows. And these are also super common in, especially like in competitive programming and leet coding and things, but also kind of in real life. So we have an array, and we want to find out the maximum subarray sum. Like if we take subarrays of size k, let's say k is 4, which for a number subarray has the maximum sum. So we can do this in a brute force way like this. We take compute the sum, so 2, we move 1 step forward, compute the sum, 1 step forward, compute the sum, and so on, right? Easy, we know how to do this. Now, can someone figure out where we have an overlapping subproblem here? Like, where could we cache this?
Cache the last 3.
Say what?
You could cache the last 3 from the first group.
Yeah.
And reuse it.
Exactly. So you see here where there is a lot of yellow, that indicates that we're doing that a lot of times. Like we're calculating, we're summing that up a lot of times, like you're saying. So instead of n times k, we can actually speed this up a lot, and especially if we have a large size of the subarray. So what we do is like this. We get the sum of the first one, and then to get the next one, we don't sum all the elements up, but we take the last sum and remove, in this case, the one we left off, and add on the one we picked up, right? So we go through this like this, and suddenly we've saved ourselves a lot of time, because now we have an algorithm that's only going to be as many operations as the size of the array. Super, super common. And this is like fairly easy to understand because we have a fixed size array that we're going through, but this is a very useful technique for many, many problems. So let's look at a problem where we can use this. And this is a grumpy bookstore owner, classic to the leet code problems. It's like a little bit of a story. This guy has some people coming into his bookstore. Every minute, there's a different number of people. Sometimes he's happy, sometimes he's sad. When he's happy, then the patrons are happy, and we want to maximize sort of like the amount of happy people we have. So we can say these people will always be happy. They're happy because he's happy. Now he has a trick that will make him happy for a certain number of minutes. We're not judging. We all kind of like can figure out what it is, but we're not judging. So let's say they can make him happy for 3 minutes. And he needs to optimize when he uses this happiness to maximize the the number of happy patrons he's going to have. Now, sorry, I'm doing like an Azure batch job right now, so I'm thinking a lot about Azure batch, but this would kind of equate to, we have a rebate for an hour, when can we put in that rebate, you know, to make sure we're cramming the most out of our rebate or something. But anyway, so what do we do here? Well, we can take away the ones that were always happy. And then we can make this into a maximum sum problem, right? Because we have this. Now we can just figure out, like the same technique that we used last time, to just figure out which subarray or which window will make us happiest. Using the exact same technique, just different storyline. Cool. So that's with a fixed window. We're going to take two more. One with a window that's growing and shrinking. So in this case, we have Amy. She likes fruit. She puts fruits into baskets. She goes around in an orchard, and she can pick, and she picks from every single tree. But she has this limitation where she can only have 2 types of fruits in her basket at the same time. I don't know. She's picky like that. So question is, how many fruits can she pick maximum? So the way we go through this is in a similar way, where we start off with one apple. We expand the window until we reach a point where our premise is not valid anymore. So in this case, we have 3 fruits in our basket, so this is not a valid window. Instead, we go through and shrink until our window is valid, and we expand it until it's invalid, and shrink until it's valid again. And we just calculate the maximum. And this is, again, an O of n of something that can be a very, very, very tricky problem otherwise to figure out, where we would have to go through, all the combinations of pick this, pick that. Finally, the last one I want to talk about is a 2-pointer algorithm, which is also a sliding window thing. So in this case, we have these walls, and we have water, and our goal is to maximize the amount of water that we can have in this container. And the walls, you see the first wall is 1 meter high, and the last wall is 7 meters high. But we can only have water until the lowest wall. Otherwise it will fill over. So question is, which walls should we use to maximize the amount of water we can use? Now, we can start off like this. We know that the widest we can make it is this. And this turns out to be, give us 1 by 8 square meters or cubic meters, maybe, of water, and depending on how deep, I guess. The only way we can make this any better is if we make it higher, right? Yeah? And the only way we can make it any higher is if we move in. If we, instead of this, we move in to the next one that's actually making it higher. So now we have 7 by 7, which is 49. And the only way we could possibly make this better is by moving the other one in. Now, it turned out it didn't make it better, but that was the only way we could possibly have made it better, right? And then in this last set, the only way we can make it better is, again, taking the lowest one and finding a better option for it. And this is a very simple way now with, again, O of n to figure out what the water is. So some of these might come to you and would come in and say, well, how did you figure that out? Well, yeah, it's not totally obvious that you should do this, but if you've seen enough problems and you've seen enough sort of different kind of variations, you can then use those and put them together. So before we leave, I want kind of like quickly talk about how I think about algorithms and how I think about coming up with these weird solutions. So the first thing that I do is I ask a lot of questions. I ask a lot of questions about the problem, and obviously when we have a leet code problem or like a competition problem, the only information that's there is whatever information is written in the text, but there is usually a lot of information there, a lot of information about like how many piles and you know what the different things are. So and also ask yourself questions like, do I need to actually simulate and know all the paths in the graph, or do I just need to know sort of like the number of paths? Because those two are two completely different questions. One might be one where you find a pattern and you can answer it, and one might be where you have to go through and do a lot of work. They're completely different. And then the limits. So the limits, for example, if you see something like 10 million or like 10 billion bananas, you know it's going to be a binary search problem. There is no way you can create an algorithm that will like effectively go through 10 billion bananas. And then I like to grok the problem. So I couldn't find another word for G, I'm sorry. But what I mean by this is like I'm trying to be the algorithm. I draw a lot on paper. I draw all the examples I can in all the different ways I can. I try to sort of like mentally think, how do I, in the small cases, actually solve the problem? If I go through and like, what do I do when I think, like, do I automatically pick the highest number, for example? Then I need to figure out how to pick the highest number, these kind of things. And then usually when you draw them out and when you've kind of like gone through a lot of examples, you get like this, oh my God, yeah, I understand. Like there is like this key moment in time when you realize that, yeah, the only way to make this water any higher is by, you know, increasing the lowest wall. Then I try to reduce the problem into its core pieces, which might be, okay, so first I need to sort the array for this to work, and then I need to find out like the highest number, and I need to do X, Y, and Z. And only then do I start to implement. I found, like in the beginning when I was doing, especially when I was doing competitions, I would go through and I would immediately sit down and code, and it would take me so long because I didn't have, like, I wasn't actually thinking through the problem before I started. And the same thing actually goes for when I'm at work. Like oftentimes I find that, like if I code fast without, you know, because I think, oh, this is an easy problem, I'll at least start it. Like I'll end up spending a lot of time on the back end because I didn't design it first. And then adding tests. So for example, like especially for these competitions, they usually have a bunch of test cases, and it's very useful to just add in, you know, like a few tests, so you can kind of like iterate over given like a number of solutions and see if it is still passing all those tests. And then you go around and be happy, and then what I usually do is I go through a lot of other people's solutions afterwards to figure out how could I have done this even better, or what other options could I have taken, or even try to limit myself a little bit more. What if I didn't have a chance to sort the array? What if I can't do this? So that's how I go about kind of like coming up with an algorithm. And just for sort of like what can you do from here? I've talked about leet code a lot. Leet code, there's a lot of sites like this. So there's like CodeForge and a lot of these different algorithm sites that give you an algorithm a day to work on, or like have these a lot of interesting problems with where you can actually type in code and then get it tested, like so it runs through all their tests and everything. And you can also go in here and do competitions. And competitions on leet code, for example, they are on a weekly basis. They have a competition in US time zone. And then bi-weekly, they have a European time zone competition. And no one else is going to know if you enter or if you end up last or whatever. It's 1.5 hours of your time in your private home, on your private, like on your computer. Who cares where you end up? But for me, it's like a fun way to see if I'm improving or not. And then, this is Dylan's moment, because I think this site, whether it's Christmas or not, this is a fantastic site. So this is Advent of Code, and in December every year, this guy, Eric, puts up like 2 challenges per day with a lot of fun backstories of used to solve algorithm problems. So if you don't want to do it the whole year, then at least in December, have some fun. And if you're more inclined to do math, there is Project Euler for math questions. But yeah, that was a lot of algorithms in 1 hour. So we have about 10 minutes or so before I have to give up the mic. So if you have any questions, I'm here. But thank you so much for coming.